Good afternoon, class. We are looking at section 3.5, the chain rule. We're going to continue what we started by looking at more examples of the chain. For example, y is x squared plus 4x over x to the power of 6, and we want to differentiate this. It's important to recognize your algebraic techniques here, that you can write this as x and this one as 4. So x plus 4 to the power of 6, and we are going to use the extended power rule. So to do that, the exponent sits in front, 6. Then you write the same thing, g of x, x plus 4 to the power of 6 minus 1 or 5. And then you multiply by the derivative of the inside, which happened to be 1, and then you rewrite it. The answer is 6 times x plus 4 to the power of 5. In this case, we use the extended power rule as well as the quotient rule. So I highly recommend you write both of them before you work on that. And so we put the 5 in front. We are looking at the extended power rule. Then we write the same thing to the power of 5 minus 1 or 4. Then we want to differentiate this using the quotient rule by writing this as f over g. And following the quotient rule. So f prime g minus g prime f prime, the derivative of the top is 2 times gx minus 8, minus g prime f, the derivative of the bottom is 1 times the top, 2x plus 3. And then you write the bottom, x minus 8, in a parentheses, and square that becomes g squared. And this is the only calculus step. We are done with calculus. All we have to do is simplify this. By distributing, we get 2x minus 16 minus 2x minus 3. These two cancel each other. These two add up to negative 19. Now, to make sure we recognize what we have, we are going to keep this number. We're going to write this as 2x plus 3 to the power of 4 over x minus 8 to the power of 4. Please see these two are the same. But it will help us with the final answer. And we're going to rewrite this as negative 19 over x minus 8 quantity squared. Now, in the numerator, we have 5 times 2x plus 3 to the power of 4 times minus 19. So we multiply these two and we get negative 95, 2x plus 3 to the power of 4 in the numerator. The denominator has x minus 8 with the power of 4 and with the power of 2. Their product will add up the exponents and it becomes x minus 8 to the power of 6. And this is the final answer. We are differentiating exponentials, and it was mentioned that the derivative of exponential is always itself. If it's e to the power of x, it's just e to the power of x. If it's e to the power of kx, it's itself times k. If it's e to the power of g of x, it's itself times g prime of x. So the way I'm going to differentiate is to rewrite the answer as itself, e to the power of 5t. And then I need the derivative of the exponent 5. I put it in front and I'm done. Or e to the power of tan x, I'm going to write e to the power of tan x. By the chain rule, I need the derivative of tan x, which is secant squared. So again, I'm going to write a few formulas and I follow them. It speeds up the process. To differentiate this, we should recognize we have the exponent as 2/3 times x. So the answer is itself e to the power of 2/3 times x. And then the derivative of the exponent will give you 2/3. And you're going to put that in front. You're done. The only reason I rewrote this, I wanted to make sure everybody can see that the coefficient of x is 2/3. So we know how to differentiate e to the power of x or e to the power of kx or e to the power of g of x. But what happens when the base is no longer e? So we want to find out how to differentiate that. So to do so, let's say y is b to the power of x, where b is a number other than e. So I'm going to remind you of what we learned in algebra. Ln of e to the power of x is x, e to the power of ln x is x, which basically says exponential functions and logarithmic functions undo each other because they are inverse functions. So I'm going to use this. If x is e to the power of ln x, then b must be e to the power of ln b. So take a look at this one. B must be e to the power of ln b. And I'm going to replace the b. Notice ln b is just a number, like 5, 1.8, you name it. So e to the power of ln b to the power of x by the power rule of exponential is e to the power of ln b times x. And ln b is just a number. And now it puts us in this format or in this format. So the answer is itself, if I want to differentiate this. So y prime is itself. And times k or times g prime, whatever you want to call it, the derivative of the exponent, which is a number ln b. So itself times ln b. Now, I'm going to put this back in the format I received that. If you go back to what you wrote here, this can be replaced by b. In other words, this whole thing is b to the power of x. And therefore, we proved when y is b to the power of x, the answer is b to the power of x times ln b. So any exponential, the answer is itself. So this one, the answer is itself, 3 to the power of x. But when you look at the base is e? No. Then by the logarithmic properties, you need ln of the base, you need ln of 3, and we just rewrite. What happens when we have 2 to the power of 7x? Similar to that, and going back to this one, remember we have to tag along g prime of x by the chain rule. So the same thing happens. If we have b to the power of f of x, the answer is itself. Then ln b by the logarithmic properties. F prime of x, the derivative of the exponent by the chain rule. Therefore, y prime, you're dealing with an exponential is itself. The base is not e times ln of the base 2. You're dealing with a function other than x, so you need the derivative of 7x, which is 7, and you just rewrite it. Let's look at some applications. Example 1. After t weeks, the number of people using a new rapid transit system was approximated by the formula n of t equals 60 squared plus 500t plus 8,000. At what rate was the use of the system changing with respect to time after 8 weeks? Because they are mentioning rate and it's one point in time, it's the instantaneous rate of change, it's n prime of t differentiate. So this will give us 12t. This will give us 500. A number gives us 0. So 12t plus 500. After 8 weeks, replace the t with 8. $96. plus 500 is 596 people per week. Units. Notice this is dn dt, the change in n, the number of people, over the change in t, the number of weeks. That's how you write the units. What does it mean? On week 8 or after week 8, the number of people using the transit is increasing at a rate of 596 people per week. Why is this increasing? Because this number is positive. If this number was negative, we would replace the increasing with decreasing. We wouldn't change the number to negative, okay? Because if you write decreasing and negative, in essence, negative times negative is positive. A bacterial colony is estimated to have a population of P of T equals 24T plus 10 over T squared plus 1 million T hours after the introduction of a toxin. What is the population after 1 hour? So basically you plug in 1. And bear in mind, if they say, what is the population after the introduction of a toxin without giving you any numbers, that means the T is 0. So at this point, replace the T with 1. 24 times 1 is 24 plus 10 is 34. This is 1 squared, 1 and 1 is 2. In other words, you have 34 over 2, which is 17. 17 what? Million bacteria. So that's elementary algebra. At what rate is the population changing 1 hour after the toxin is introduced? Now, rate refers to either average or instantaneous. 1 point in time, that means instantaneous. That means a p prime of a t, and that requires the use of a quotient rule. So we're going to call this f. Over g. So f prime is simply 24 times g, which is t squared plus 1, minus g prime is simply 2t, times f, the numerator is 24t plus 10, and then just write the bottom, t squared plus 1 in a parenthesis and square it, g squared. Done with calculus. We're going to continue with algebra. So we're going to distribute, and the numerator is 24t squared plus 24 minus 48t squared minus 20t is to add up to negative 24t squared. So we want p prime of 1. So replace the t with 1. P prime of 1. Replace the t with 1. So of course 1 squared is 1. Minus 24 minus 20 plus 24. This is 1. So the numerator is simply minus 20. The denominator is 2 squared 4. We get negative 5. Negative 5 million bacteria per hour. Remember, this is the dt, the units of the numerator, population, over the units, the denominator, time. That's why we get -5 million bacteria per hour. What does it mean? The population of bacteria is decreasing at the rate of 5 million bacteria per hour, 1 hour after the toxin is introduced. Why decreasing? Because this has a negative sign. And notice we don't mention this is -5, just decreasing at this rate. Because decreasing means negative. It is implied. Example 3. Observations show that the length L in millimeters from nose to tail of a Siberian tiger can be estimated by the function L equals 0.25 W to the power of 2.6, where W is the weight of the tiger in kilograms. Furthermore, a young tiger's weight can be estimated in terms of its age t in days by the function W equals 3 plus 0.21 t. How long is a tiger when it's 100 days old? Well, there are a couple of different ways of approaching it. One approach is that you plug in t equals 100 here to find the weight. This has 2 decimals, 2 zeros. They cancel each other. They result in 21. With 3 is 24. So the weight is 24 kilograms. You always answer with proper units. You put the 24 into the L function as a function of W. Use a calculator. And it results in 969.369 millimeters. So this thing was an elementary algebra in essence. Now, what I want to remind you of is that in the metric system, one meter is 100 centimeters or 1,000 millimeters, meaning this is almost 1 meter, or at least it's very close. At what rate is the length increasing when it is 100 days old, the tiger? And we have the rate, we have 1 point in time, that means differentiation. So the length, so dl, and this is time, dt. We want dl dt. I'm going to write it in this fashion, and I'm going to remind you dy dt is dy du du dt, where u is the intermediate variable. So notice L is a function of W, W is a function of T. So going from L to T, the intermediate variable is W. That's where you put that dW, everybody. So dL dW times dW dt. Leibniz's notation. So with that being the case, what is dL dW? It's a simple case of a power rule, 0.25 times 2.6 times W to the power of subtract 1 from 2.6. That means 1.6. Then we want dW dt. Before we go there, let me just make sure you understand this part, everybody, is this part. And what is this part? dW dt. You want to take a derivative of W with respect to T. It's just 0.21. In other words, this is simply this. And so if I multiply the numbers 0.25, 2.6, and 0.21, I get 0.1365 W to the power of 1.6. If the question was to find the derivative and not necessarily after 100 days, you really have to change the W to 3 plus 0.21 T to make this a function of T. But since we want it after 100 days, it's 100 days old, And we know W, when the tiger is 100 days old, is 24. We can replace W with 24. Use a calculator. And it gives you 22.0532 millimeters per day, the LDT, the units of the length over the units of the time, millimeters per day. By the way, this whole thing is an estimate. That's why you can even use less decimals, whatever that they ask you. The whole thing was estimated because even over here it mentions the weight is estimated. And you're done. What I want to show you is the second method. And the second method is that this, you can make it a function of t. So how do you find that? The composite function, replacing the w with this statement, 3 plus 0.21t expression. Therefore, L of a t, L as a function of t, is 0.25 times this expression, 3 plus 0.21t to the power of 2.6, and work on this. So right here, if you replace the t with 100, that gives you part A. Of course, this part you already know is 24. Put it into a calculator, and it gives you exactly the same answer as you got in the first place. So we have L of t. If we want to find dLdt or L prime of t, we differentiate this using the extended power rule. How do we do that? 0.25 times 2.6 times the same thing to the power of 1.6, right? 2.6 minus 1 times the derivative of the inside, which is 0.21. So again, 0.25 remains. 2.6 sits in front. Same thing to the power of 1.6. The derivative of the inside is 0.21. And if I multiply this number, and this number, I get 0.1365. This one, and this one. And as you can see, these two are identical. If I change the W as I mentioned before, to 3 plus 0.21t, I get this one. And right now, if I replace the t with 100, I get the same answer that was found here. All right, the amount of glass recycled in the community is G of P equals 0.5 P squared plus 7 tons, where P is the population in thousands. It is estimated that T years from now, the population of the community will be P of T equals 4.4 plus 0.1 T squared thousands. How many tons of glass are expected to be recycled 4 years from now? Well, you put the 4 into this and you find the population first. 4 squared, 16 times the 0.1 is 1.6. With 4.4 becomes 6. And now you plug in 6 into G of P, replace the P with 6. This is 36. Half of it is 18, plus 7 makes it 25. So square root of 25 is 5 tons of glass. Find the rate at which the amount of glass recycled is changing with respect to time 4 years from now. Of course, as always, you have to include units. So we want dGdt because we are referring to the rate in one point in time. And I'm going to write it in this fashion, reminding you of Leibniz's notation. dy dt is dy du dt. So I want dGdt, and I'm going to write it in this format. As we go from y to t, the intermediate variable is u. As we go from g to t, the intermediate variable is p, so we need dp. Therefore, we find dg/dt, and then we find dp/dt. The product is the answer. So first and foremost, in order to find dg/dt, we're going to write this as 0.5 p squared plus 7 to the power of 1/2. To differentiate this, we use the extended power rule. So 1/2 sits in front. Same thing to the power of 1/2 minus 1 or negative 1/2. The derivative of the inside, 0.5 times 2p is p. So a quick recap, 1/2 sits in front. Same thing to the power of 1/2 minus 1. Now, by the chain rule, I need the derivative of the inside, 0.5 times 2p. So this is 0.5 times 2p. So that's dg/dp. What about dp/dt? Take the derivative of this expression with respect to t, 0.1 times 2t. 0.1 times 2t makes it what? 0.2t. So 0.2t. Now, we have calculated p to be 6, and t is, when t is 4, p is 6, according to the previous step, we are going to use them. Therefore, replace the p anywhere you see p with number 6, and replace the t with 4 anywhere you see t in this expression. In other words, do I have to simplify this because I'm evaluating it? No, I don't have to. If you want to simplify, you can, but just plug in and it's just as fast. So what happens when we plug in? We get 1/2, 0.5 times p squared, which makes it 6 squared, plus 7 to the power of negative 1/2 times p, which is 6, 0.2 times t, which is 4. This expression, remember we did that. This is the same as this one, and it's 25. So this is 25. So 25 to the power of negative 1/2 is 1 over square root of 25, or 25 to the power of positive 1/2. So this expression, which is 1 over 25 to the power of positive 1/2, or 1 over square root of 25, is 1 over 5. And therefore, what you have here is 1/2 times 1/5 times 6 times 0.8. So again, 1/2, 1/5, 6.8. This gives you 4.8 divided by 10, or 0.48 tons of glass per year. dg/dt, the units for dg/dt, the change in the amount of glass, tons of glass, the change in time in year. Now, we could have used the composite function g of a t, replacing the p with this expression, as we did in the previous example. So g of t is 0.5, a p squared is 4.4 plus 0.1 t squared to the second power, plus 7, and work on this. However, if you want to differentiate this, it's a lot more difficult than this one. So it is important to know both methods. And in this case, the Leibniz's notation, it's an easier way to differentiate.